Okay, welcome everybody. Good afternoon. How are we doing? Okay? Semester's starting to pick up a little bit. This is week 3. Administratively, are there any questions? Do you have any questions about what we're doing, how we're proceeding? Logistics? Okay. Good, because I'm going to throw out a couple of things. If you look at the syllabus, there is, how do you say it? A category called lab, okay? And we are working on getting the lab up and running for you all, okay? And it will be based pretty much essentially on what we covered today and Thursday. Okay, we're going to be doing material properties, and the lab will be an opportunity to do some tensile testing on some materials. We're going to start those sections up a week from today, on Tuesday. Okay? The way that's going to work is you will sign up for a section which is actually during class, okay? Because we didn't put a lab section, right? So we're not going to try to, mess with everyone's schedules at this point. So what's going to happen is 9 of you. There'll be 3. If we get it right, there should be 3 testing stations, okay? And we're going to have 3 people per station, okay? And so 9 people per session will get to do the lab. And the write-up is not intended to be extensive. This is not, you're not going to be doing a large lab report, but you will be getting to record some data and be able to enter the answers on Canvas, all right? So be up for that. We'll be sending out some information later this week, and there will be signups. Any questions? Yes?
Do you have previous tests we can look at questions?
Absolutamente, yes. Where are they, everybody?
The website.
On the website. Okay? So if you go down, good question, okay? Because I probably didn't say it formally. But if you go down here, you'll see that there are 1, 2, 3, 4, 5, 6 exam 1s, 6 exam 2s, and I need to upload a 6th final exam. Okay. So yes. All right. So there are many questions. Yes.
You should more like the more recent years.
Yeah, I would start with the more recent years and then work back, if you like. And then please forgive me for the earlier years, okay? So that's that. Any other questions? Good question. Okay. Well, what are we talking about today? What are we talking about? You tell me, what are we talking about? Yes?
How do we sign up for lab?
What's that?
How do we sign up for the lab?
Okay, so we will post that. We haven't posted it yet, but it will be a Google form essentially. And so if there are 2 other people you want to work with in the lab, sign up for the same slot with those 2 other people. Okay? And if there's 6 other people you want to work with, or 8 other people you want to work with, try to all converge on one section. Okay? But there'll be teams of 3 for your assignment. Yes, up there.
Can we use Colab for midterms?
Can you use what?
Colab.
No, I'm afraid that okay, good question. Question is, can you use Colab? Can you use Desmos during the exam? No. Okay, but you can use a calculator, and you can be a graphing calculator, and you bring in a page of notes. So front and back, 8.5 by 11 or A0 or A4. I don't know, whatever the one is, yeah. not like a big poster, right? That, you know, you can, no. So just that's what you get to bring in. Is that okay? Okay. Other questions? Good. All right. So what are we talking about? I'm asking the question now. What is today's topic? Okay, material properties. And what about material properties? Sorry, I can't look and write at the same time. What material property or what material properties are we emphasizing today? Yes, Zach. Elasticity. All right. That's such a good word. Makes you sound so smart. Elasticity. Okay. And then, you know, people ask me, hey, what do you teach at Rutgers? And you know what I tell them? No, I don't say elasticity. Because actually, the people who are teaching graduate mechanics would probably be offended. Because elasticity is like this really technical, fun thing with lots of math and tensors and stuff, which we don't really get into. All right. I tell them I teach a class called Mechanics and Materials, and another title would be Why Things Break. Okay, that's pretty much one of the things we do. But today we're not talking about why things break too much. We did that a little bit last time when we talked about stress and strain. Actually, well, yeah, we will talk a little bit about it today, I guess. We're going to talk about how materials respond under tension. And what would it be like if every time you wanted to understand how a geometry of a certain material behaved, you had to go and test it? Like, I have to go put the whole Eiffel Tower in a tensile testing machine to see how it responds. Is it going to fail? Is it going to break? Right? That'd be really silly. Okay? So what we do instead is we take little chunks of materials and we test them. Okay? And when you test them, we look at we do measure force and position, right? And then we convert that to stress and strain. Okay? So this is, and you know, you've probably watched the video, so I won't go through all this, but these are the kind of apparatuses that you might have for tensile testing. So in this case, this is a compression test. Okay, so there's some concrete in there. This is a tensile test, so it's being pulled apart. All right, this is being compressed, right, to be clear. And this is a tensile test under tension as well. Okay, and what you typically have is a large section for the gripping, and then you have the test area, okay, or the gauge area, okay. Why would you put a larger chunk in the grips than in the section you're actually measuring? Yes, Kevin?
You want that area to purposely break. And
Yes.
So if you make it all a consistent width, and there's a lot of inconsistency in exactly where it will break.
Yeah. Yeah. So you're designing it so it breaks in the middle region, right? This is the narrowest area or cross section. Okay. And so for a given force, right, force divided by area, the stress is going to be higher in this central section than in the thick regions. Okay. So when you do your lab, you're going to have an opportunity to put little tensile test specimens in the machine, and you're going to grip them and you're going to pull them apart. Okay? And you're going to hope that they fail in the central region. Okay? The reason there's this curve here, okay, and we don't cover this in this course, you'll cover it in design mechanical components. The reason that exists is so that you avoid a sharp edge. Where there are sharp edges, there's what we call a stress concentration. So the effective stress at an edge ends up being much higher. Well, it can be like a factor of 2, 3, whatever, higher. And so that can lead to undesirable tearing at that location, okay? So sometimes you think, oh, well, all those smooth, nice curves, they're just for decoration. They actually serve a purpose, a mechanical purpose. I mean, they also look nice, right? Don't do what I did when I was a senior. I was a sophomore. I was working on a project, like it was a class project where you had to like build something, and so I had to like do stuff in the machine shop and blah 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 and like make this thing. It didn't work very well. Fortunately, I didn't get a bad grade in the class, but I didn't do very well in the contest. So, but like I handed one of the parts that I made to my professor, and he almost cut himself on it. That is not a good way to impress your professor or your teacher, right? So it's often good to smooth those rough edges as well. Okay, let's keep going. So yes, we are talking about elasticity, and I'm sorry, we are going to talk about things breaking too. Okay, so what happens when we plot stress versus strain? The material initially behaves like a spring, meaning you can go up and down this portion of the curve. Okay. This is the linearly elastic regime. Linearly elastic. Now, if you keep pulling on the material past a certain point, it yields, right? If it's a ductile material, meaning it's got some softness to it, right? It's not necessarily super brittle, okay? Then it will stretch a lot for the same amount of force or stress that you put into it. Okay. So you see, this material, the slope is very high here, but it actually kind of flattens out. Okay. And so the slope becomes less. That means you can get more strain for a given amount of applied force or stress. Okay? So strain is on this axis and stress is on this axis. Now, you do see something called strain hardening. Okay? So what's going on here? This is an interesting behavior. So I just said you get more bang for your buck. True and not true. For your sample, okay, it's the force can be increasing, and then like you get more measurable strain there. What's happening is you get as you get to a certain point, you get necking. But what's happening here is that you have the introduction of what are called dislocations. So when you take mech props or material props, right, you'll be able to learn more about what's happening at the material level. Okay, but this strain hardening, okay, is an interesting property in that you're introducing these dislocations. The material is continuing to go, and when you release from that region, okay, you're going to come down at a different location. Okay, so this is, don't worry about the 0.2% here. Just think about, okay, I'm strain hardening, and then I come down here. I've introduced dislocations. The material may not look very different, but there is actually going to be some amount of permanent strain. Okay, it's plastically deformed. So I wouldn't say that the cross section has changed a whole lot at this point. All right, because that's what happens in necking. Okay, where it actually goes down, when the slope goes down. Okay, but what's interesting here, is that when you come back down, you've got some permanent strain. So the sample is longer than it was when you initially pulled it or compressed it. Well, in this case, these are tension. Well, yeah, and stress. Well, it depends on how you look at it. let's just say it's tension, right? So it's a little bit longer. And guess what? If you were to pull it again, it actually remains elastic up to a higher level of stress and a higher level of strain. Okay, so you've strained harder. This material is now actually stronger than it was previously. Any questions on that? Any questions on strain hardening? Yes.
So once it's stretched,
Yes.
it's going to be able to withstand more before or be able to stretch more before it starts deforming. But it's going to follow the same graph. It's just going to go back up to the same point.
Correct. So one slight little thing, but you're on the right. You got it. This is all deformation, right? We have elastic deformation and we have plastic deformation. So what we're saying is that this will go I can now go up to this point and come back to this. I can go up and down this curve, okay? Without plastically deforming it. And I won't have plastic or permanent deformation until I get up to this point 4. Okay, this point 4. Does that clear it up a little bit? Okay, yes.
So it starts to the right on the strain axis. Does that mean, like, after the first time you stretched it, it is now permanently longer, you're not touching it?
Yes. Yes. So as long as you stay, so if you go between points 1 and 2, or even point 3, okay, and you go back down, you go back right to where you started. Okay, it's a nice linearly elastic spring essentially, right? We've talked about bars as springs, so you go back. If you go past this point of no return, okay, then you come back down with the same slope. Okay, and we'll talk about slope in a second. All right, you come back down with the same slope, but see, this thing had already banked over, so you can't come back down to the same spot. Right? You're always coming back down to the same slope, but where you start your return matters. So if I start my return on that initial elastic line, I come back down to where I started. But if I get over the bend, okay, then it will be permanently deformed. Okay. Now, and you see that 0.4 is above 0.2, right? And that's why we say it's stronger. It has a higher strain. Now you can do this at the local level, all right? And you'll talk a little bit about this in DMC as well. You can actually permanently deform the outer surface of a material mechanically with essentially like putting lots of divots in it, okay? This is the one way of doing this is called shot peening. Okay, so like you can shoot a lot of balls at it on the outside and it will cause permanent deformation, which actually increases its yield strength on the outside. Okay? Now, there are other things you can do with heat treating that aren't mechanical. Well, heat treating, I mean, heat is mechanical, right? But not introducing deformation, okay? That also changes the strength of the material. But what's cool about shot peening and even some of these heat treatment techniques, like quenching, so you get it hot and then you put it in a bucket and you quench it really fast, is that it makes the outer surface stronger. And you're like, wait a second, who cares? Why don't I want the inside to be stronger? I want the whole piece to be stronger. Well, yes, often we do, okay? When we look at, not so much in tensile testing, but when we look at shear, shafts, twisting, right? We talked about shafts already. When we look at bending, beams, turns out the highest stresses are usually at the outside. So, these properties, this graph is not representative of every material. I should be careful what I say. But steel is a wonderful material because steel behaves like this. All right. Okay. What's the E? You guys have done, some of you have already done some reading. What's this E for? What's it called? Okay, yes, epsilon, okay, epsilon over here is strain, okay? E, capital E, is the Young's modulus, or the modulus of elasticity. Okay? And I can write it real big, but this is the formula. Okay? This is what you want to be using in the linear elastic regime. This is only describing the behavior here, right? And it's a first order line with a y-intercept of 0. Okay? 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 So this is the line. Typically, we are designing for us to be in the elastic regime, right? We don't want to go above the proportional limit, or we don't want to go above. Let's see, where is the graph? Yeah, this one, the yield strength. Okay, right here. Now, look, in practice, when you look at a material spec sheet, people are not going to say this is the proportional limit, this is the elastic limit, and this is the yield strength. They're going to report the yield strength. They're close enough that you just, for our intents and purposes, usually, I mean, I might say proportional limit, but if you see yield strength, then yeah, just use that, okay? I mean, I don't think I've designed a problem where I try to make you distinguish between these three, okay? If you go past the yield strength, proportional limit, if you go past the elastic limit, that's when you get permanent plastic deformation, okay? But if you go past the yield strength, which is usually past the elastic, it's going to be past the elastic limit, that happens too. You'll see in steels, it does this interesting little dip, okay, and then it starts cranking up again. The ultimate strength is the maximum stress the material can handle. For steels, we end up using this value some as well. Okay, it can be SU or sigma U. We use that a lot when we're talking about fatigue, actually, for some approximations. And then fracture stress is the stress when the thing breaks. Okay. Sometimes you might design for this, but usually you're designing to be less than the yield strength. Any questions? All right. Okay. So with that, go ahead and start working on the problems. We'll be going around, okay, and to answer questions, and we'll also do attendance in a second. You have a technical question or a general question?
It's about the
What's that?
For question number 5.
Okay, it's a question? Okay, but hold on. Give me a minute, please. Okay, so you can go ahead and do your attendance if you like right now. And Yeah, so that's the easy way to do it. I mean, you can compose expectation like say, but in reality, well, you have to kind of by area. So X2 is force. X bracket 2 is force. Right? If you want to do it right, as the calculation, right? And so the force is on the axis, just square root of 2 times. So you square root of 2 times area, or we can solve that here. So we have X
There that I got.
well, I would assume I would No, it really
And they,
okay.
I got that,
We were just doing this.
I'm still not. This is the.
No, that is so that
I'm the force, yeah. Sorry. I'm not getting this. Like, I don't know what
So
else
we
to say.
have, so next paragraph, right? So, that's what's. So the force is X bracket 2. It's just okay, so time okay. That's fine, we meant times 0.01, that's fine. This is times 10 minus 2, whatever you want to do, let's say times 1. Okay. Yeah. You gotta run the top like.
Why don't you just do that? Makes it so much easier.
That's right. So if you know the notes, right, and you use method of sections or method of joints, calculate it's a bunch of math. So that's easy. So you should know how to do that. Yeah, so I just. There are two ways to do it. You do method of sections. You haven't watched it. That's all the way back in. It's all back in.
In my opinion.
Well, sections is there if you care about trying to figure out one method. And we were only trying to have 5 minutes on numbers, so you're right. Do you have a question?
Yeah, it's from last session.
Yes.
Is this one, I'm having trouble understanding the, like,
Yeah.
stuff behind this.
Okay. So this is just a question about the convention.
Yeah.
And nomenclature, right?
Yeah.
So the first subscript. So first of all, tau means shear stress, right? Which means that we have a force acting along the surface, right? The first subscript is the
X-face?
the phase. The second subscript is the direction. Okay? So this would be tau xy would be the x phase in the y direction. Right? So yes. Now what we also do is we talk about equilibrium, right? And if you look, you just have the notes up, right? Tau xy or tau zx is equal to tau x. Okay? So this one, and this one, and this one, and this one, they're all actually the same magnitude. Okay? And if we care about, so typically what will happen is I'll write out tau xz here, and then I know that all these, in order for the element not to be rotating, they all have to be equal. Okay, and that's what we do in the notes. Okay, so now if you go back to that quiz, that question, and if you've already got it right, don't resubmit it.
No, I haven't gotten it right yet.
Oh, you haven't got it right. Okay, that's fine. Because if you resubmit it, actually no, this is due today, right?
Yeah,
By 7.
seven, yeah.
So let me take a closer look. Okay, so yes.
Y-X, negative Y, negative X.
Okay, yeah. And it turns out, okay, that you can also sigma. Remember we said you could write sigma, right? But we don't write tau. And I didn't talk about it in class, but the Einstein convention is that you could use instead of letters. So this is like saying, this is like sigma yx, this is sigma xy. sigma is the same as if it's
So
a
one
different.
is X, two is Y.
That's right. That's correct. So those would count as Y.
But is this not,
We don't normally use that convention,
oh,
but in this class we won't use that. We won't use that convention normally. Sure.
Okay,
Yeah,
okay.
but so those two are equivalent.
alright.
So let's see. This is a Z, right? It's hard to see sometimes, right? So it's not Z. All right.
Thank you.
And your name is
J.
Jay. Okay.
Because I don't even take it too serious.
Yeah. You know, if you did the
We're
homework
all
and you're bored and
We're
it's
in mechanical techniques. We're all
you should,
mechanical.
share the love, okay? All right. What's up? Yeah. So, yeah.
But there's so much stuff that's so far.
What I put on your desk. But you need.
So all you do.
Here, it's there. You can use that, and then you can trade me. Or you can.
Look, I have like the whole entire.
Okay. I'm gonna go take Yeah. All right. So there.
Yeah, but you can't include mechanics next semester.
Okay. All right, so there's a question. Actually, there's been multiple people have asked about the collab. All right. For session 4. Okay. Okay. All right. So if you go back to the notes for session 2, you'll find how to attack this very same truss problem. Okay? Right here. All right? The goal, the question in the homework is, what is the stress in this member, right? Member 3. So what we have to do is figure out what the axial force is. And then once we figure out what the axial force is, we divide by the cross-sectional area and we get the stress, right? It's force divided by area. So there are 2 ways to do it. There's method of joints and method of sections, all right? Either, and I go through, I think we went through it last time, and I think we also went, and of course it's in the video, so you can go through that in detail. Either way, method of joints or method of sections will give you the following. That the force is the square root of 2 times P. So P is that downward load, and force F3 is the internal force in that member, okay? Now, another way of doing this is to use linear algebra and to use the collab, right? And so that's what people were wanting to know. So here you go. First, run the first part, and then you come down over here, all right? And maybe you have, I don't know, 1,300 newtons, okay, of force in your problem. And then maybe you have 1.1 centimeters as your diameter, okay? Now, what I would do to make, well, actually, what I did actually easier than that is I just made it 0.011, and I changed this to meters, all right? But if you want to keep it like it is, as I put it, we can just define D again and say, right, would give us it in meters. Okay? So now, after that, we go through, and I don't expect you to really go through know how to do all this, right? But in the notes, actually, it's there, okay? In the notes, we show that we can come up with a set of linear equations and come up with a matrix and come up with forces and then the external loads, and we can figure out what these forces are. Okay. Actually, this is the external load, and it's different depending on the equation we're using. All right. So what comes out here is this x2. This is actually the force in member 3. Okay, that's the force, but that's not the stress. To get the stress, what we have to do is take that force and divide by area, right? And then, or I could do this on my piece of paper and just say square root of 2 times p is that force, and then divide it by the area. Well, what's the area of a circle? Huh?
Pi r squared.
Pi r squared, right? Or pi d squared over 4, right? So now, I take the force, and I'm going to write an expression for the area, and maybe I should make it bigger so people can see. And the expression for the area is going to be pi times the diameter squared. Now in Python, this doesn't work. All right, you have to do double asterisks, and then you divide by 4, and that's it. Okay, and then it spits out the answer. Note, maybe take it for granted, the code also is giving you the answer in megapascals. This answer is in pascals, right? And to go from pascals to megapascals, we had to divide by 10 to the 6 or multiply by 10 to the minus 6. Okay? Hopefully that will be helpful. Right, we're going to post, there will be questions and answers for the lab on the end. So it'll be like another When we'll sign up, that will be also going to post an announcement.
Yeah, and then that at the end, like, what to do and just follow.
So there will be, we will get with you with the video. Okay, it's going to be fun and adventurous.
You know what I mean? Like, some people write, like, for classes, they like write like literally step-by-step instructions of something that they already created, and we just have to recreate it and then write
It'll be, if I can get it to work in the next couple days, it will be a fun. Yes.
That helped, thank you.
All right, good luck. Yeah, so everything is going to be in a different section. So record everything here. Right? I'll say that. And
Remember you helped me to register my class? That I said to you on the Friday, so I'm going to register this class. Now I'm going to.
now it's okay. From the start. Yeah, okay. All right. Thank you for your time. Any questions? Okay.
Yeah, so I think that's really good. Oh, so yeah, I just did
It's not all privilege like
Okay, by sound. Okay, you can do this now.
like people that was like this year are paying 700 like a house.
Alright.
Why would you live?
No, it's okay.
Yeah.
You know.
If you have a car, part of that. I'm saying like.
And there's the elastic. Okay. You normally do all of these. They're about all the same. They're all the same. Most of them. But they have different definitions, right? The force element is when you can go beyond the force element, and I mean, it's like, it's no longer, right? No longer like. It begins to bend slightly, but it was really like to come back down and on less than elastic. The elastic. And the real change is when the material is moved. It's also very I'm not gonna use mine. So, you can put it into your tip to know files. Other questions?
This is so awesome.
No, I'll tell you. Do that. At some point, I just or you just
It's not Isaac, I'm trying to find it yet. So we're calling the library, but or non-class, and then into dot and then five. Yeah. MATLAB and Python are actually very similar.
The rule is not, no, the number's not right. Okay.
We will in that. Okay.
I got question 5 right, but I guess mine had the same.
Whatever numbers you got.
So as you move it around, take a course along, of course, but because we need small information, things that okay. Right. The yield. Yes. Oh, well, that's the, yeah. Good job. Yeah. Good question, good question. So, yeah, you can't, it's not quite like you can make it infinitely strong material just like a continuous spread. That'd be nice, wouldn't it? You get a pattern on that. Questions, yes? That is delta. Delta. Like delta. Okay, so it's for displacement. Or deformation. So what you're saying is because like you say delta, that's all right. Okay. Actually, I'll be in a second. I was still back to the code here. Just give me a second. Oh, that's so bad.
You can copyright it.
Well, some people, I previously related this to the community video.
Yeah, I'm sorry, I got it.
One message was the right thing. Alright, so this problem, there are a couple things where but you need to like the answer is and I'm using the force energy. Okay, so in this case, x, I'll make brackets 2, that's the force energy. But what we need to do to calculate stress is y by 5. Alright? So, to do that, you do force divided by 5. Now, the next of the, like, just the little, this is actually works until or not works, just difference between that. Okay, so we're going to say this that's what we use. Okay, it has to use the numpy library that goes to 3, and then it says, okay, so that's 3.4. And then where it's not unitary, it's actually that's square. It's also the just like semantic. You know, you guys are doing that. So you can do it, you can like do representing that 5 stuff. You can say like, you know, 5 times 3 times d times 201 squared. Or multiply by this, multiply by or you just have to. Alright, no problem. And your name is Jake, and you are, okay, I'm not going to do all that's only take like the original Zelda. Yeah. I was like, Any questions? Questions?
It's right here.
Okay, so
It's the same one, but it's like, it has.
So there are a couple ways to do this, right? So if you go back, yeah. Right, so this one they choose the observation. So L is L is the that's the force what do you know? You know the K, right? So we can actually include that EA over L. Okay. So we would have to find that. Right. Well, yeah, I guess so. Or you could say, or you can say that, E, right? L divided by A. Write it out. No, on paper. You gotta be, everything you got on paper first, and then it got. Okay, so let's, okay, let's write for me, right there. Okay, L, and then A, right? So the way I would do this is I write 144 and I would actually, I would probably do this from the different, right, so I can mention that now. You can't do it? No, I did not. Yeah. Yeah, so that's, so this is not hard. We all make the same count. We all gotta, you gotta like, you know, right? So, like, we want.
No, the numbers were not. Oh, no.
All right, so.
Oh, I didn't get it right.
I would put it in, I did that part. So I want this, I want to say it too. I want the thousand left. Okay, and then and after 1,000, after 1,000 millimeters. Yeah. Yeah. So now, okay, I will scribble this out. Alright, so now millimeters equals millimeters, so I would cross them off. And kilometers equals kilometers, so cross them off. Okay, and then I have meters over meters, but this is about. I'm going to do calculator. I would say equals 144 times 76. Yeah, okay. And then I would remove 2 meters. I did all that work. That's right, okay? So that's that one. Now, I need area, right? And I'm probably going to do area. Units, right? So that one's a little bit different on 2, right? What's the area? So that's yeah. Well, yeah, this is an inquiry problem. I'm not sure my And then you can say in.
No, I know. That's like the yeah, you said that's
Right? So, yeah, make sure you won't have this on now, right? But, okay. All right. Do you ever think that like people with multiple pages and do it so?
I trust your
Oh, you don't have one yet. I just didn't use, I used that. I'm rated for
Well, that he does have some symbolic meaning, right? I didn't actually be honest with you, but do you see on the, yeah, but do you see on the slide, I can say, right, I forgot to put this on the yeah, I didn't see it. And what do you mean? Let me ask you. So we have slides. The session 5. The slides. Okay. I would work in symbols first. No, don't do that. You can get a answer. I'm not saying you better. That's not fair. So if you look now, it says easy retail. So I lean towards the shop. Okay, the area. Okay. I don't know. It was like it was yeah.
I don't know that guy. Yeah, he said that. I don't know. I signed him.
So, we're looking at the scene. We need to figure out what so this is a bar that is in, so what's going to happen to that? Well, it will be, things will be. It's possible, okay, but I also don't know.
Exactly.
I needed
100
to like that. Oh, but if you didn't put a negative, yeah.
What I did was I took,
Yes. And then divide by the last one. Figure out the string. Yes.
Then I multiplied by percentage.
That's good. And then you gotta multiply by the diameter.
And yeah, then I did that, and then I did.
Okay, well then, that's
So it
probably.
was a side.
I'm guessing, I have that in my guess. I mean, it could be, what is the seed is the rule of succession, right? I understand, right, so, but, yeah. Yeah, you don't use the money. But you do use that answer. Your name is? Yes, okay. Gracious. At least, I mean, I can double check. You did all the other things you just said?
Yeah,
Oh, okay.
check the units and everything.
Yeah, okay.
I do this from,
All right, everyone. Thank you for coming today. Have a good one.